Okay, so yeah, I'll just say it again. So there is a quiz, so do the quiz. There is a recitation today, which is 4 to 5. And homework is due next week. You should be able to do all of it now. There was some, I thought, so on the last quiz, there was a kind of interesting question about if you have two carbons. It showed you a little picture where you had these p orbitals and you had these so-called sp2 orbitals, and these are p orbitals. These are carbon centers. This is for this molecule that we were looking at, ethylene, which has a double bond and a bunch of hydrogens attached. So the hydrogens are kind of out here. Maybe I'll put the hydrogens in blue. And then there's a bond that forms between two of the carbons. That's the single bond, this one, and it forms between two of these sp2 orbitals. And then the double bond part, it actually forms this pi bond, which kind of overlaps the two p orbitals on top and bottom. Like that, makes a delocalized state. And I asked where the shapes come from for the s and p orbitals. Well, in the notes, it mentions that when you look at solutions to spherically symmetric potentials, remember that the solutions are always going to be proportional to the spherical harmonics. And I mentioned that the L equals 0, 1, 2, 3, and so on. They're given special names, which is just the S, P, D. I guess the next one is F or something. But in any case, S and P just refer to the L value of the spherical harmonic. And the reason they're shaped that way is just because if you have an electron at a single carbon center, well, this is just some Coulomb interaction between an electron and, however many protons are in here, and whatever your atomic center is. So it's just the problem for a single center is just basically the Coulomb potential again, but we already solved that when we looked at hydrogen. So that means that the solutions are going to be proportional to spherical harmonics. So if you look at the angular distribution, which is what the spherical harmonic tells you about, the L equals 0 is going to be spherically symmetric. That's the s orbital. That's spherically symmetric orbital. Then you have the L equals 1 states. Those are going to have lobes like this. And those are the p orbitals. And how many are there? Well, it's L equals 1, so there's 3 m values, 0 and plus or minus 1. And so there's 3 different kinds of p orbitals. There's the ones that sort of go up and down, and there's the ones that go kind of out like this. And then there's the ones that go sort of left and right. It's just the 3 directions. And that's what happens here. And the reason these are called sp2 is it's a linear combination. It's a sort of called hybridization of the L equals 0 and L equals 1 states. So it's labeled sp2. It's a combination of s, which is L equals 0, and p, which is L equals 1. These two p orbitals combine with the s to form kind of, a triply shaped kind of orbital, and that's responsible for, connecting up with the s orbitals of the hydrogen out here, and then this guy right here that helps form the sigma bond with the other carbon center. And then, of course, the leftover p orbital that helps form the double bond. So everything about chemical bonding, you can understand a lot of it by just looking at the solution to the hydrogen. And that, it's, again, goes back to spherical symmetry. If you have spherically symmetric potential, which is what you would have if you have a single atomic center and an electron, that's a spherically symmetric situation, then your solutions are given by functions that are proportional to spherical harmonics, because those diagonalize the angular momentum, which is for spherically symmetric potential, your kinetic energy is just going to be the angular momentum operator squared. It's going to be the angular piece of it. So yeah, and then when you have multiple atomic centers, of course, there's going to be some interaction between them, and that'll change the eigenstates. But that's why we had that model where we assume that interaction between the adjacent atomic centers is sufficiently weak. And so then, to a good approximation, your bonding states are just going to be well approximated by just using that basis of bound states at each carbon center or at each atomic center. But if you think about the spatial structure, of course, it's nothing but for a single atomic center, just the solution to a spherically symmetric potential. So that's what I was hoping you would think about, is connecting what we covered in class, right? We did the radial potentials first, and then we did that model for molecular bonding, but they're related, of course. The first part of what we did tells you about the spatial structure of what's going on in the second part of what we did, which is, using the simple model of weakly interacting kind of atomic centers. Any questions about that? You can even sort of look up in the wiki, right, what atomic orbitals look like, and here's the different shapes, the p orbitals and the s orbitals. And here are those hydrogen wave functions that we talked about. And so here's the p orbitals. Of course, the n number matters too. That tells you about what's going on in the radial direction as well. But you see the angular part here is just proportional to the spherical harmonic, YLM. So hopefully you see the connection there between chemistry and rotational symmetry, and which allowed you to solve the hydrogen wave function for the hydrogen wave functions. Yeah, so here they are, the various SPD. Yeah, the next one is F. That would be L equals 3. But then if you just look up spherical harmonics, see it's the same same shapes. This is S, this is P, this is D, this is F. So the spherical harmonics tell you about how two atomic centers can bond with each other. If you start thinking about how, the different spherical harmonics can overlap. So you can have a sigma bond, that's would be like two s orbitals overlapping and making a delocalized state. Pi bonds, have these p orbitals overlapping. And that overlap, that's just corresponds to having that linear combination of bound states, right? In our toy model. Okay, so I wanted to go over that again because most people didn't really get that. So, any questions about that? Okay, it's also kind of fun. You can actually look at arbitrary configurations of, hopefully, I don't know if you guys see that. My computer is a bit frozen. Hold on a second. Can you see that Mathematica notebook? I think my computer's kind of, for some reason, not doing it. Okay, there. That should work now. So what you can do is you can generate a random molecule just for fun. And how that works is you just generate a random matrix that's symmetric and it has, say, ones along the diagonal. Those are the bound states. And then on the off diagonals, you have -1. That's the hopping term. Of course, you can change these to make the, you typically want the bound state to be bigger than the hopping term. So you can make the bound state larger, like 10 times larger or something. So here we, so here we have -1 for the hopping term here. And it's symmetric, of course, then 10s along here on diagonal. Remember what I told you, that this matrix, if you ignore the diagonal, the bound state part, that just corresponds to the links between, in this case, there's 10 atomic centers. So you can actually make Mathematica try to figure out what it looks like. So you can actually have a plot of that matrix. So here it just puts nodes for the number of dimensions you have, and then puts little links wherever it has a connection in the adjacency matrix, where it has a -1 there in that corresponding matrix element. So you have a molecule like this, and then you could ask what's the eigenvalues and eigenvectors of this thing. And of course, you can make Mathematica do that too. And you'll get a bunch of energies, right? And so for a single electron, of course, if there were no interactions, then there'd be it could sit in any of the centers, right? Here, 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 here. And all those would have energy 10. But because of the ability of the electron to delocalize across the structure, you can get much smaller energies. So you can get all the way down to 4. And you'll get typically some smallest ground state here. It's much smaller than, say, 10. And that would correspond to a very delocalized state, meaning that there's like a little bit of probability density at each center. And so you see, this is the eigenvalue, and then the eigenvector is this thing. So you see it's got some non-zero here values basically at each center. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 centers. So there's like it's an evenly distributed sort of density here across the different centers. And you see that's why you want this hopping term to be negative, because you want the slowest state to be a kind of symmetric combination. What happens in the higher order for these higher energy states, the excited states, you'll get like anti-bonding, they're called states, where the probability densities add with opposite signs. So you see, here we go, the state with almost twice as much energy, this guy, it's still delocalized, but you see you get minus signs for your elements of your eigenvector. You get minus signs and some plus signs. So there's like an anti-symmetric combinations of the probability density across different centers, sort of positive on one and negative on the other, just the combinations of the bound states. So yeah, that's it's kind of fun to do this. I don't know, it's just sort of, you can see, you can just try out different random structures or invent your own. It's kind of cool. Mathematica always sort of figures out a nice way to represent it. And you just make it spit out the eigenvalues. And again, there's the lowest one that's much smaller than 10, and it's always some mixture, some symmetric combination of all the bound states, right? And then the higher order states are, again, anti-symmetric combinations. So yeah. Okay. I spend a lot of time on it, but I want you to get it so that you sort of see what's going on. And then these bound states, again, the bound states, the spatial structure of those at each carbon center, the things that actually form linear combinations to form bonds, those things are just basically look like, you know, the hydrogen atom solutions, because each individual center, the bound states of that, you know, if you ignore the interaction, then the individual bound states, the basis that we're using, those are just the given by the solutions for the Coulomb potential, because an electron just sees the atomic center as just like a center for a Coulomb potential. Okay. All right, so that was a little aside, but sort of related to the quiz from yesterday, or from 2 days ago. Okay, so we're back to approximation methods now, and we're doing the variational method. And last time where we left off was we were doing an example, and our example was the infinite square well here. And we know the exact solution for the ground state. That's just this cosine. Then you have the lowest energy here. It's given by h bar squared pi squared over 8ma squared. And then we were trying to see if what we can find if we try to use the variational method for this kind of trial wave function. And again, this trial wave function, it just changes the shape of the hump. So if it's like parabola, then alpha, you know, is 2. If it's got like a cusp thing like this would be alpha's 1. If you make alpha even smaller, it'll start being really cuspy. And if you make alpha even bigger, it'll be just really flat at the top. So this is like, it'd be like that. So you're just changing the shape of that hump. And the first thing we did was we determined the normalization. So normalization was given by this integral. You can integrate the square of the trial wave function. It has to give you 1. From that, we're able to generate what n is. And so this is where we left off. This is our trial wave function. And so now what remains to be done is calculating the expectation value of our Hamiltonian with respect to this trial wave function. So our Hamiltonian, of course, is just the kinetic energy. It's a square well. So when you're in the well, you're just a freely moving particle with just some kinetic energy. So it's minus n squared. So I'm going to put back the n squared. It's the integral over that well, minus a to a dx. And then the psi star part is, of course, absolute value of a to the alpha minus x to the alpha. And then you have the kinetic energy, which is h bar squared minus over 2m, minus h bar squared over 2m, two derivatives with respect to x acting on the trial wave function again, which is a alpha minus x to the alpha. So that's what it is. Now you just have to be careful to evaluate the absolute value properly. So again, this is symmetric across 0. So you just can cancel this 2 over here and have this be minus n squared integral from 0 to a of dx. And now a is positive, so we can leave that go. And now x is positive 2. And now you have, we can pull the h bar squared over m out. Let me just do that. The minus sign's still there. And you have two derivatives with respect to x acting on a to the alpha minus x to the alpha. So you just start applying the derivatives, and you get, can multiply through by the minus sign, h bar squared. We can put in the n squared. That will give us an alpha plus 1 and a 2 alpha plus 1 divided by 4m alpha squared, a 2 alpha plus 1. Then you're left with the integral from 0 to a dx. And now we just have to do the derivatives, and we can multiply. So this is just two derivatives acting on this guy. This is a constant, so it's only this guy that matters. So this minus sign cancels this one out here. So those minus signs cancel, and you get a to the alpha times alpha minus 1. And then it's x raised to the alpha minus 2. And then you get the same thing, minus x to the alpha. That's this term right here. Alpha minus 1. X to the alpha minus 2. So I just multiplied the stuff out. And now you have to do the integral of these two terms. Of course, this alpha here combines with this alpha. You get 2 alpha here. Get rid of that. And you just do the integration. You get h bar squared, alpha plus 1, 2 alpha plus 1 over alpha squared, 2a alpha plus 1. And then you get, from this integration right here, you get what happens. Well, you have to do this integral, so you divide by alpha minus 2 plus 1, which is alpha minus 1. So you just get a to the alpha, and then a to the alpha minus 1 coming from this x, and then all of it is divided by alpha minus 1. And I'm going to pull out this factor of alpha times alpha minus 1 just outside of everything in a moment. But do this. This guy becomes, I have to pull down a factor of 1 over 2 alpha minus 1. So this becomes divided by 2 alpha minus 1, just from this exponent up here. And the thing up here just becomes 2 alpha minus 1, like that. And then all of this is times alpha minus 1. So you can actually combine denominators here. And after a little bit of algebra and some cancellations of, first of all, there's a cancellation of these 2 alphas. This 2 alpha cancels these 2 guys and this guy. You get another factor of a in the denominator, so you can cancel this -1 up here and make this a 2. So you get something over a squared. And then the other factors, they reduce to, well, first of all, let's write out what we know. It's h bar squared over 4ma squared. You see it has to have the same units as the solution we had before. And it does, h bar squared over ma squared. So that's good. We have that. And we'll have to see if that number out in front is going to be close to pi squared over 8 or not. After we minimize. So you have this, and then the rest of it is just alpha plus 1, 2 alpha plus 1, and divided by 2 alpha minus 1. That's just after doing the algebra of these alphas and canceling stuff out. You can sort of see what happens here. So one of the alphas gets canceled like that. Then you can just multiply this out and just simplify the expression for alpha, and you end up with this. Okay, so that's good. And now you just have to minimize this. This is some function of alpha. Remember, this is our expectation value of h as a function of alpha. And you just have to solve dh d alpha is equal to 0. And, alpha, it's got a pretty simple kind of form, right? It's no big deal. You can even, it's easy enough that you can plot it and see that it only has, nothing funny is going on with it. So let's see. You can see here, this is a plot of that expression, and you see it'll have, now something funny happens here where the expectation value goes negative. So clearly there's something funny happening when alpha is equal to 1/2. But away from that, that's a sort of pathological function anyway. It's sort of a very cuspy trial wave function. But outside of that, where we'd have this just something bad happening here, there's a minimum here at around, well, it's a little bit below 2. A little bit below 2. And that's where our optimal value of the expectation of the Hamiltonian is. So that's where we would expect our local minima. Everywhere else is sort of, we won't find any critical points anywhere else. So that's fine. So that's good. If we do the first derivative test, we're sort of guaranteed to find this point. And you can do that. And I'm not going to bother with this kind of tedious taking a derivative of this stuff, but you find that alpha star, the minimum, occurs at 1 plus square root of 6 over 2, which is about 1.72. Right, a little below 2. So the shape, as promised, is kind of close to a parabola. That makes sense because you know that the real shape is supposed to be a cosine. But, so you get something sort of between these shapes. So closer to a parabola shape for the hump. And it's supposed to, most closely approximate this cosine. And now you can ask, what about the ground state energy? Is it close or not to the true ground state? And what you can do, you plug in for the variational method. You just plug in for alpha star up here, and you'll get that according to the variational method, this thing is close to 1.2374 h bar squared over m a squared. And the a0 exactly is, again, it's h bar squared pi squared over 8ma squared, which is about 1.2337 h bar squared over ma squared. So in terms of these units, the h bar squared over ma squared units, you see it's just different in the fourth significant figure. Really remarkable. You know, very powerful. You can get the the ground state energy just a little bit off from the true one. And moreover, you even know, because of the variational principle, that this number is going to be bigger than the real one. So you even know the direction in which you're going to be off from the true value. So in that sense, very powerful method. You can often get just really close to the true value, and you always know the direction which you're going to be off. You're always going to be larger than the true value of the ground state. So yeah, and this is the example. You see, it's kind of tedious to work it out, but you can use Mathematica and stuff. It's not, the integrals themselves are not problematic. They're just powers of x, but there's just a lot of alphas running around, and when you include the normalization, and then you have to actually do the derivatives, it just gets a little bit tedious. There's just a lot of alphas running around, so you have to use a chain rule. But I don't, you can just use Mathematica or something. Okay, any questions about that? So that was the example. Okay. I'm going to clear then. So maybe some of you are wondering what else you can do with the variational method. How do you get the other eigenstates? Obviously, we just found the ground state. That's the lowest state. What about, what if you wanted the higher energy states? How do you get those? That's trickier. That's not a common application for the variational method, but you can do it because if, say, you wanted an approximation for the first excited state or something like that, you know that the eigenvalues, that the eigenvectors are going to be orthogonal. So you know that the ground state dotted into the first excited state, that's going to be 0. So that means what you would want to do is you just want a trial wave function which again is some state that depends on alpha. You want a trial wave function such that the ground state dotted into the trial wave function is 0. Because if you were to do that, then whatever you get for the trial wave function, it's going to be orthogonal to the ground state. And so if you go through that argument again for the variational principle condition, what you'll find is that this time the variational principle would say that it's the first excited state that's going to be bounded by this expectation value if this holds. It's because if no component of your trial wave function is along that eigenstate direction that corresponds to the ground state, then the only possibility is that the linear combination that goes into phi alpha doesn't have any component that's along the ground state. So you can go through that argument again, and you'll see that now instead of this being the lowest state, it's as if the excited state is sort of the smallest you can get, because there is no component along 0. So you don't even get that in your summation. So you can go back and just see that that's the case. So if you pick something orthogonal to the ground state, then you're actually going to be bound by the first excited state. So that's how you do it. And sometimes you don't know how to do that. You don't know how to construct one because you don't know what the ground state is, right? But you can often use symmetries to do it. For instance, you might know that the ground state is an even function. So then for your trial wave function, you just make sure that you pick an odd function because the inner product between an even and odd function is just going to be 0. So you can do it based on some symmetry. Typically even and odd functions for sort of spatial problems, that's common. Otherwise, maybe you'll just have to settle on using your variational approximation for the ground state. And just ensuring that your trial wave function is orthogonal to your trial wave function that you used for the ground state. So that's another way you could do it systematically. So that's how you do it. And then for the next one, if you want to do the next state, what you would do is you would just use for E2, you would just find a trial wave function such that it's orthogonal to both your trial wave function for the ground state and your trial wave function for the first excited state. You would just find something like that. So that's basically, that's how you do it. But that's rare. It basically doesn't come up very often that you find the excited states using the variational method. Just doesn't come up very often. Variational method is usually used to find the ground state. But still, you could do it if you wanted. So this is for E1. You would just find a trial wave function such that this is true, or this, if you don't know how to do the first thing. And for E2, it's the same thing, except you just have one more constraint that it's also orthogonal to the first excited state. Okay, but I don't think I'll ever ask this. At most, I might ask you approximate. Like on a test or something, I might ask you to find the first excited state, and then you would use something like the fact that the ground state is an even function, something like that. Okay, so that's the variational method. Any questions before we move on? And indeed, the program that that Mina mentioned last time does indeed do this process for you. So it actually calculates the expectation value that you need, and and then it uses a classical minimization routine to minimize it once you have the expectation value. It's sort of an iterative process. So that's so there are definitely software packages available that you don't really have to do much other than specify the Hamiltonian, and the program does the rest of it for you. So that's pretty cool. Okay. Well, the next major topic for approximation methods is perturbation theory. And it really requires a kind of solid understanding of eigenvalues and eigenvectors to really get it. But the basic idea is the following. You have your Hamiltonian, and you have a piece that you can diagonalize, and you know everything about it. You know its eigenvalues, which we'll label like this, and you know its eigenstates. And the eigenstates might be degenerate. So we put a little r there to label the degeneracies. So if we know the eigenstates, the eigenvalues and eigenvectors, possibly degenerate. Then what you do is you assume everything else is a perturbation, something small. And so W is our perturbation, it's an operator. And then what we do is we expand everything in terms of this parameter lambda. And this is our expansion parameter. And whenever we see any expressions, we're going to try to Taylor series them, around small lambda. So actually, just given that alone, you can actually, if you're sufficiently kind of comfortable with vectors in Hilbert spaces and expanding in a basis and so on, then you can actually just derive from scratch all of the formulas for perturbation theory. It's not really a big deal. All you need is this basic setup. So it's important to remember this basic setup because everything else you can actually derive from kind of first principles. So what is it that you want to derive anyway? Well, you want to know what the actual energies are. And you want to know what the actual states are. And maybe I'll call those phi n. That's what you want to know. And well, you don't want to, again, because this is our expansion parameter, we want to know them as like a Taylor series in lambda. So we know that, first of all, the energies, if lambda is 0, then there's just the unperturbed ones. And then we want a Taylor series where we go order by order in lambda, where these are the higher and higher order corrections. So that's what we want. And for the state, it's the same thing. We want, something here, and then we want a Taylor series in terms now of vectors in your Hilbert space that correspond to corrections to this unperturbed state. So you can already see some problems that might happen. If, for instance, these guys are degenerate, right, and the eigenvalue here doesn't change depending on R, then as soon as you add this, maybe all of a sudden, all this perturbation now, maybe that'll be able to separate out different values of R and give you different energy levels. So it's kind of tricky when you have degenerate states. Moreover, it's unclear as you send lambda to 0 and these corrections disappear, which one of these NRs do you go back to? Because they're all degenerate, so there's no way to choose among them once lambda is equal to 0. So there's sort of, you have to be careful when there's degenerate states because this perturbation might make them non-degenerate again, like break the degeneracy, and you have to be careful with that. So that's why the two cases are treated separately typically. But we'll see how it goes. But in any case, once you have this setup, you can sort of now just go through the calculation for just figuring out what these corrections are. And the reason you can do that is just because you already know what you want, right? You know that if you take your full Hamiltonian and act with it on the full state, the fully corrected state, then you know that this is just going to be equal to it's just the eigenvalue equation. So that's it. And then since you know that you need an approximation like this, you kind of just go from there. Instead of h, you first of all replace it with your perturbation. So this becomes h naught plus lambda w acting on phi n. And then instead of e, you would put en 0 plus lambda en 1, and so on, phi n, right? And then you would replace your states with your Taylor series. So this gets replaced with, and I'm going to drop the r, I guess, for now. We'll deal with degeneracies later. Okay, so we just replaced the eigenvalue equation. We replaced it with the approximations that we want. And of course, this is for arbitrary lambda. So this equation has to be satisfied order by order in lambda. So you can look at the smallest power of lambda, solve that equation, and go from there. So of course, if there are no lambdas, then this equation to 0th order, when you drop all of the lambdas, then the 0th order equation is just exactly what we would expect. It's just the eigenvalue equation for the unperturbed Hamiltonian. So now you look at the linear terms. And again, because lambda is arbitrary, this equation, it has to be, every single power of lambda has to match on both sides. So what happens to leading order in lambda? So the first order. So h naught hits this lambda here. That gives us one term. So this is h naught acting on phi n1. What else? You've got this lambda w hitting this n. And what do you have over here? On the other side, you have, you have this guy here hitting this guy over here. So you have lambda en 0 phi n1. And then you also have plus lambda en 1 hitting this n right here. So what do we do now? Well, this is an equation that has to be satisfied to this order in lambda. Of course, we could just get rid of the lambdas now, because that's a bookkeeping device to make sure we have all the terms of the correct order. And if we just look at this equation, this is a sort of vector equation. But you can sort of see how we can extract something. We can extract, for instance, we can extract the first order energy correction. And the way we can do that is we can take an unperturbed state, M, some other, we can take the unperturbed state N rather, and we can dot it into this equation. And what do we get then? We get this is just a constant that comes out. And here we get just well, N dotted into N, which is just 1. So this, though, what's this? Well, this H can act on the left, and that'll pull out another factor of this guy. So actually this cancels that. And this just becomes 1. And so what you find is that the first order correction to the energy is just given by the matrix elements of W evaluated the expectation values of those with respect to the unperturbed eigenstates. Great. So what about this equation tells you more, though, of course, because, well, we know that any, so again, where your knowledge of Hilbert spaces comes in handy, we know that any state like that, any state in a Hilbert space, we can decompose into a basis of the unperturbed eigenstates, where the coefficients are just these inner products between m and phi n. So as long as we know these coefficients, we'll know the state. And you can get the coefficients by now dotting in with an arbitrary m on that side, right? You get m h naught phi n 1 plus m w n is equal to e n 0 m phi n 1 plus e n 1 m dotted into n. So, okay, so you have to be careful. This mn gives you a delta, Kronecker delta, right? It's either 0 or 1. It's 0 if m is not equal to n. If m is equal to n, then it's 1. And so we can now solve for these coefficients, right? These guys right here. This h naught, again, can act on the left, pull out a factor of em naught, the unperturbed eigenvalue. And so what do you get? You can, this becomes em 0, right? I can pull this guy over to the left-hand side to get minus en 0. And then it's just a coefficient. And then you get these guys. All right, so what do you get? Let's see. Oh, you get this. Let's see, this. Right, so now you can plug in for this guy, right? This guy right here, we already know what it is. It's just this guy right here. So that's equal to, we can write it as follows. It's delta mn minus 1, and then it's m w n. Why does it work? Because for this term, it's only non-zero when m is equal to n, and in that case, this becomes nn for this term. And so that's just the first correction here. Otherwise, this term right here, those are includes all the terms, including the off diagonals that just came over to this other side, and we subtracted off as minus 1. So now you know what these coefficients are. And so you can divide through and substitute back into the expression for the state. what do you get? You get phi n1 is equal to sum over m 1 minus delta mn over en0, or sorry, e m0 let's see. So I flipped the sign here, so this is now en minus em. I put minus signs on both sides, so this becomes 1 minus delta m. This becomes en minus em. Divide through like that, and you get mwn, and this is the coefficient of the mth along the mth direction, the unperturbed direction. So look, this is nice. Whenever m is equal to n, this part vanishes here, which is good because this would be 0 too. That's not good. So this vanishes whenever m is equal to n. So this reduces to a sum over all the m's that are not equal to n of just m wn en0 em0. And that's the first order correction to the state. And you see the problem that degeneracy gives you is if you have degenerate states, then some of these m's might actually give you the same energy as your nth state that you're looking at. And then you'll have a problem because this might blow up. Right. So that could be an issue. So that's why you have to kind of treat the degenerate case a little bit more carefully, which we'll do in a moment. But yeah, any questions about that? There's nothing particularly fancy about what we did. It's just a lot of algebra. You just say, I want the eigenstates as a Taylor series. I want the states as a Taylor series. I know that the unperturbed states form a basis for my Hilbert space. And so I can just figure everything out from there. I can start with the eigenvalue equation. I can write down what these things are in terms of their Taylor series, and then I could match both sides order by order in lambda. And at each order, I will get an expression for the energy, which I get by dotting in with the unperturbed eigenstate here. And I'll get an expression for the state by dotting in with an arbitrary unperturbed state, so I can get the coefficients of my state. Like that. So, and you could just do that order by order. And, you know, it gets uglier the higher order you get. So if you do it to lambda squared, what you end up finding is that the second order correction to the energy is now a sum m not equal to n of the absolute value of mwn squared over so it has that form. The second order correction to the states is hardly ever used, so I won't write it down. But we'll talk about this a little bit more generally. We'll talk about perturbation to sort all orders. But before we do that, let's do an example real quick. So let's do an example. But any questions about this development so far? Again, if you're ever on a deserted island and you forget perturbation theory, you just have to go back to what it is that you want to do. You want to find the eigenvalues, you want to find the eigenvectors order by order in some small parameter. And literally, that's all you need to remember, apart from the basics of Hilbert spaces, which we sort of, really tried to hammer in the first semester. After that, it's just like algebra and just solving things order by order, and then you just figure out what the formulas are. You never have to remember these, really. I mean, of course, it's kind of annoying to have to rederive them every time, but anyway, but there's nothing more to it. The final expression may look complicated, but conceptually speaking, there's nothing new here. It's just vectors in Hilbert spaces and expanding in a basis, and then doing a Taylor series. That's it. Okay, so the example is unperturbed Hamiltonian is just a harmonic oscillator. And remember, these things had eigenstates n, right, or is the ground state, and the unperturbed energies were h bar omega. There's a ground state at h bar omega over 2. But this is a harmonic oscillator ground states. And suppose our perturbation is lambda w. Suppose we had a, with the appropriate units, it would be m squared omega cubed over h bar q to the 4th. Suppose we had a quartic perturbation. If you think about it, that means perturbing the harmonic oscillator potential, which is like a parabola with a q to the 4th term, which, obviously it's going to get very big at large q. So you see, you can try to make this lambda really small, but you'll probably always fail, right? Because this thing is blowing up real fast with q. It's always going to overwhelm this guy. So that's, and you can see that when you actually try to compute the corrections to the energies. So if these are your original energies, then the first order correction in lambda, that's just going to be the matrix element of the W with respect to the unperturbed eigenstates. And you can use the, creation annihilation operators to write out the what Q is. And of course you can raise it to the 4th power and do the kind of thing that we did last semester. He actually had this kind of thing on the final, I think, where you can rewrite the position operator in terms of creation annihilation operators, the raising and lowering operators, and then you just figure out these matrix elements. And after you do that, you'll find that it's this is the form of it. It depends on n, and you see it just grows quadratically with n. So that's not good. It's terrible correction because it'll get larger and larger for larger n. And that, of course, makes sense because the larger n's correspond to larger energies of the harmonic oscillator, right? So that means this thing is sort of oscillating back and forth with larger and larger amplitudes at larger n. It's got more and more energy. And at larger energy, it's of course going to sample a larger, range of q's, which is a coordinate. And so the q to the 4th potential is of course always going to win out. So these corrections for sufficiently large n are always just going to win, no matter how small you make lambda. So in some sense, when you write down this Taylor series for the energies, you might ask if it has like a radius of convergence or something, or if it makes sense even to think about an infinite series like this. And sometimes it doesn't. Sometimes the radius of convergence is 0. That for any finite lambda, if you include more and more terms, you might just get an energy that grows out of control. So it's tricky, and but we use it anyway. We just say, well, maybe if we cut off this series at some finite number of terms, it'll still give us a pretty good approximation to the energies at any finite order. But there are issues of convergence and things like that associated with perturbation theory. It's a subtle issue about whether or not it makes this Taylor series makes sense. But we're going to do it anyway, and this is sort of oftentimes the best handle we have on complicated Hamiltonians, right? We will often get the situation where we have a Hamiltonian we know, and then it's perturbed somehow. Also common, this is often the hydrogen atom, and then we perturb it with some kind of field. So that we'll do that too, I think. That's the Zeeman effect and so on. But we want to develop these formal things first. But this is a basic example of how of a first order correction. And you can see already in this basic example, you can lead to it can lead you to some interesting problems, like the fact that this just keeps growing with the n. Okay, so that's the example. Now we can be a little more general and think about the whole series in general. So like, what about all the perturbations at once? So it's sort of perturbation to all orders in lambda. What about that whole series? Is there any way to think about it? And there is. So what we can do is we can take our eigenvalue equation and we can rearrange it a little bit, and we can rearrange it as follows. We can put the unperturbed eigenstates over here and the unperturbed Hamiltonian off to one side, and that's acting on phi n. You can put that on one side. And on the other side, what we'll have left is the lambda w that comes that came along with this h naught before, but now it's just lambda w. And we're also going to put on this side the true eigenvalue. And we're going to add back the unperturbed eigenvalue. So this whole thing right here is sort of minus that Taylor series of corrections. It's like the rest of that series. It's the full thing plus with a minus sign plus the unperturbed one. So that's the rest of the series, and all of that on phi n. So we can rearrange it like this, and then what you can do is you can choose a particular normalization for your fully corrected states. You can choose, and it won't be a standard normalization where the states are like normalized to 1. They're going to be chosen such that n dotted into phi n is 1. It's the appropriate normalization to choose for doing perturbation theory to sort of higher orders. You can later fix the normalization, of course. Once you find your perturbed states, you can later fix it to be, phi n is equal to 1. But you can do that later. At first, you just assume that this is true and then find your solution for phi n, and then you normalize it afterwards if you want. So, okay. And if you choose that normalization, then stuff kind of simplifies, right? First of all, I can act with both sides of this equation by, on the left by n, and on the right-hand side, I'll get phi n 0 minus so if I act with it on n, right, I will just get I'll just get 0 here. So this will just give me, if I act with it on the left with n, then I'll just get en0 minus en0, because this is the unperturbed Hamiltonian. So that'll just give me 0. And on the right-hand side, I have to be a little bit careful. What will I get? So if this whole thing is equal to 0, then what this guy here, I will get a lambda and then n w phi n, which I'll leave alone for now. And then I'll get minus, and I'll get, these are all constants, so I'll get minus en plus en 0, and then, well, okay, so let's see, what's a nice way to, right? So maybe I'll put a minus here, I'll put all this in parentheses, maybe I'll put a minus in here. Yeah. And then out here, I'll just get n phi n. And we're going to choose this normalization so we can drop this part. This is just going to be 1. And all this is equal to 0. So what does it mean? I can just put this over on the other side, and what I'll get is en minus en0 on one side. And what is that anyway? Well, I told you that that's the rest of the series. That's like the lambda en1 plus lambda squared en2. That's like the rest of the Taylor series. That's all equal to lambda n w, and then this is the corrected state. And what's that? That's like the Taylor series of the state. Phi n1, and so on. So you see, this formulation tells you that the Taylor series for the energies is, of course, related very closely to the Taylor series for the state. You can write one in terms of the other. So when we do this kind of state correction and energy correction, it's often given to you as sort of separate things, and you just memorize the state correction, you memorize the energy correction. But you don't have to. They're actually just very closely related to each other. The relationship is just that. If you now look order by order in lambda, it's pretty obvious what's going on here. This power of lambda corresponds to a term here that's 1 less power in the state correction. So here's the state correction, but this overall term is proportional to lambda. So the lambda squared term is the first state correction, and that is related to the second energy correction. So if you just compare these term by term, order by order, you'll find that the mth energy correction that corresponds to lambda to the mth power, that's just n w dotted into the state correction that's 1 less order in lambda. And you can check that that works for the expression as I gave above. It's just a general property of perturbation theory. And in fact, now I don't even have to do that whole business of going out to second order in lambda to get this, right? I don't need to do this anymore, because I showed you quite generally that the second order correction is related to the first state correction. So I can just take this NW and stick in the first state correction, which I did calculate explicitly. It's right here. Stick that in, and what you'll find is exactly this. So you can just take that formula I just derived here and just use, En2 is equal to, again, N W dotted into the first state correction. And you'll see that it works out. It'll work out to get the W, this matrix element squared business. You just use this formula applied to 2. So now I don't even have to do the whole matching of the Taylor series coefficients anymore. So okay, that's important. And I'm out of time, but next time we'll continue working on this and sort of getting intuition of how the whole series looks like. And then we'll do a sort of self-consistent perturbation theory, and then we'll talk about the degenerate perturbation theory case. And that'll kind of wrap it. I think one more lecture on perturbation theory is probably going to be sufficient, and then we'll move on to WKB. And after that, we'll be done with approximations, and we'll move on to more conceptual things. But yeah, I think that's good for today. Sort of give you a flavor of perturbation theory. Again, it's just conceptually, it's just Hilbert spaces and Taylor series. It's any questions?